So today we talk about the chapter 9, the nonlinear problems. So in this chapter, there will be a lot of mathematics, and we will tell you how do we solve the nonlinear equations using different algorithms, and it's better you know all of those algorithms. So when you use the software, you will know which one you should pick, which one you should use, and what's the difference between different algorithms. Okay, so now first let's have a look at some concept. First is the nonlinear problems. What are the nonlinear or linear problems? So the linear elastic problems including the following. The first type is the string displacement relationship is linear. So the displacement is small, so we say it's a small deformation. Second is regarding to the material. So the stress strain relationship is linear, so it's a linear elastic material. Third is the stiffness equation. So we have the linear stiffness equation, and those are three linear problems, linear elastic problems. And those are the simple case. And in the reality or in the real engineer problems, we have to encounter the nonlinear problems. So there are several types of nonlinear problems. So let me introduce you those nonlinear problems, so you can notice in the analysis which one to use or whether to judge whether it is linear problems or nonlinear problems. So the first nonlinear problem is the geometric nonlinear problems, which means the string displacement relationship is nonlinear. Okay, so it's for example, they have a large deformation or large rotation and displacement, and we will talk about the geometric nonlinear problems in chapter 11. Okay, also this is a large deformation of the beam, so this is a large for the large problems is nonlinear problems. And the second is the material. So we have nonlinear material, so which means the stress-strain relationship is nonlinear. So for example here, if we go to the plastic stage, it may be nonlinear, and also if we say the plastic deformation, the behavior of plastic deformation is a nonlinear problem. Or for the hyperelastic material, we have mentioned about hyperelastic material, and the stress, and it's the strain, and the stress strain curve is a nonlinear curve. So it's for the hyperelastic problems, it's also a nonlinear problems. And the third is the nonlinear contact. The contact problem is always a nonlinear problems, because we know here, for example, in a car crash, during the contact or during the crash, the contact area and the contact force is changing nonlinearly with the time. Therefore, this is a typical nonlinear problems, and most of the contact problems, they are nonlinear problems. So whenever you meet the contact problem, you will know it is nonlinear problems. So for the nonlinear problems, we have to set up the nonlinear equations. And the structure nonlinear analysis is converted to solve the nonlinear equations. And so for example here we have a nonlinear equation, and the stiffness matrix and the nodal force matrix are function of the displacement. This we already know this, and it's much more complex than solving the linear equations. So for solving the linear equation, we have done this by hand in our previous chapters. But for the nonlinear equations, we have to use some special technique or some special algorithm to solve those nonlinear equations, and it's very different as for solving the linear equations. So here I list several methods for solving the nonlinear equations, and if you use the software, you will also notice, okay, many times the software asks you to choose which algorithm or which method you should use for your analysis. So it's very good to understand those algorithms. At least you should understand the key idea of those different algorithms. So let's have a look. The first algorithm we will talk about is the direct iteration method and the modified direct iteration method. And the second is the Newton-Raphson method and the modified Newton-Raphson method. The third is incremental method. So in this chapter, we will mainly talk about those methods for solving the nonlinear equations. So the first is the direct iteration method. Direct iteration method. Let's have a look at the idea. So the direct iteration method starts from an initial trial value and calculate the next values using the previous values until the convergence condition is met. Okay, this is the idea. So they start from an initial value and then they do the loop, they do the iteration, and until the convergence condition is met. So we have a nonlinear equation like in this kind of form, and then we rewrite in this form, and then the equation becomes like this, and then we start our iteration. Okay, we start our iteration. The unknown variable we try to solve is A. A is the variable we want to solve. So using the direct iteration method, so we assume the initial trial function. We assume the trial function, initial trial function, and then we find the approximate solution. So we have this initial value, and then we put back into the equation, right? Put back into the equation, then we can work out the next value using the previous value. Okay, and then we do the iteration, and after every solution we check the convergence condition. Okay, if the convergence condition is met, then we stop the iteration. If not, then we continue with those procedure and to calculate the next value and then iterate again. Okay, so we can say for this method we need to calculate the inverse in each iteration, because here we see it's the inverse. We need to, in order to work out the A value, the next A value, we need to calculate the inverse of the matrix. Therefore, it's a very low efficiency. We mentioned this many times, because the K is a matrix in the finite element analysis, and it can be a very large matrix. And for the program coding, if you want to calculate the inverse, it will take a lot computational power. Therefore, there's no efficiency here. Okay, so this is the direct iteration method. So let's have a look at the iteration procedure for the direct iteration method. So using the graph here, so this is our equation. This is our nonlinear equation. In here it represents a nonlinear curve. The red line, okay, is the nonlinear equation. So we start from an initial value A0. We start from the initial value A0 equals to 0, and then we determine the next value. By using this. Okay, by using this. Actually, it's the line. It's a line. We draw this line. Okay, we draw this line. This is the first line. We draw this line, and the slope is K. The slope is this. Okay, the slope is this, and then we get this point. Okay, this is the point. This point. This point is to meet the equation. Okay, we get this point, and then we determine the next value. Okay, then get this point, and then this is our next value A1, and then we have to determine the next value. So we draw another line. We have draw the another line pass through this point. This we draw another line pass through this point. Then we get A2. Then the intercept is another point. When we draw it again, we draw the line again, and then we get A3, and we keep doing this. So we keep doing the iteration, and we can see this point, this value A3, is becomes very close to the solution we want. Okay, so if we keep doing the iteration, it will be very close to the solution we want. So in the end, we can say the iteration will converge to the solution. Okay, it will converge to the solution. So this is the procedure. This is the procedure, iteration procedure for the direct iteration method. And we say this is a convergence case, but there's in some cases they have the problems with the convergence, so it will not converge to the solution. It will divergent. So let me say here it's a divergence case. So we start with an initial value an. So we start with an initial value an, and then we draw the line. Okay, then we intercept with the nonlinear curve, and then we have an plus 1, right? And then we draw the line again. We draw the second line. Okay, we draw the second line. Then we have then we have the an plus 2. Then we draw here. Then we have this point. Then we draw the third line. Then we draw the third line. Then we have an plus 3. So we can say it's hard to converge. It's hard to converge to the true value. The true value is here. Hard to converge to the true value. So for this case, if we use the direct iteration method, we cannot convert to the true value. Therefore, in this case, we cannot solve the nonlinear equations. That's why in the program, so in the FE software, sometimes you will say you get a problem, it cannot converge. And in that case, you should change your method. You should change to Newton Raphson or other method to try the calculation again. Okay. So let's move to the modified direct iteration method. The modified direct iteration method. So for the modified direct iteration method, we use the constant stiffness matrix to avoid calculating the inverse of the stiffness matrix. So in the previous method, that is the direct iteration method, we said we have to keep calculating the inverse of the stiffness matrix, and that is make the calculation very expensive. But here we use a constant stiffness to avoid the calculation of the inverse. So again, we see the graph. Let me see what's the iteration procedure. So first we start with the trial value, an initial trial value, and then we get. Then we do the first iteration, and then we have this line, and then we get A1, the intercept. Then we get A1. Okay, then we get A1. So when we calculate A1, we have to do the inverse. We have to do the inverse once, but the difference is here. But in the subsequent iteration, we don't calculate the new inverse, so we keep using this value as the slope of the line. So this is our slope. You see this line is parallel to this line, and this line is also parallel to this line. So which means we're using the same slope. Use the same slope to do the iteration. Okay. So by using this idea, we don't need to calculate the inverse of the stiffness again and again. So we already used the previous one. So using this idea, let's see how it iterate to the solution. So then this is the A1. Then we use the same slope, and we get A2. Okay, then we get A2 here, and then from A2 we use the same slope, and then we get A3. And then you can see if we keep iterating, then it will converge to the true value here. Then it will converge to the true value here. So, and when it converges to the true value here, the convergence condition will be met, and then we will stop the iteration. And for example, if not converge to the true value, then the convergence condition will not met, and then we keep going the iteration. Okay, so this is the modified direct iteration method. So the main difference is they use the same slope as used for the first iteration, so they can avoid the calculation of the inverse of stiffness matrix. Therefore, it's more efficient than the direct iteration method. Let's also have a look at the convergence problems or the iteration procedure. The iteration procedure, actually we have already explained. Okay, so let's just repeat this again. So we give initial value A0, and then we determine the line. We determine A1. The next step is determine A1. So A1, from the initial value, we can calculate the A1. Okay, we can calculate A1. A1 equals to those, and here is the line. So we find the A1, and then we need to calculate A2. Okay, then we calculate A2. So A2 is A1. So it's A1 plus delta A1. Okay, plus delta A1. Here the delta A1 we can calculate as we use the same slope. Say this is the same slope, and then we use it's small, so then we use Q. This is Q minus those value. Okay, this here. So then we use this distance, and then we get delta A1. And then we can find A2. Okay, then we find A2. So we assume the step. This is the step from A1 to from A0 to A1, A1 to A2. They are small. Then we have those. Okay, then we have those. Okay. Examples for the direct iteration method. So this is a nonlinear equation. We have the nonlinear equation. It's our nonlinear equation, and the Q equals to 3, and this is the formulation for the nonlinear equation. We can write as this format. Therefore, it's easy for the direct iteration method. So if we write in this format, then the Kx equals to minus x plus 4. Okay. So we start from the initial value. Okay, some people may ask, so we start from the initial value, so maybe the convergence will depend on which initial value we choose. Okay, this is true. Okay, this is another disadvantage of the direct iteration method, because if you choose different initial value, and your convergence speed may be very different, and in sometimes if you choose a not appropriate initial value, and then you will get you cannot converge to the solution. Okay, so the initial trial solution is important. So we assume the initial trial solution, and then we start the iteration. So here we are using the direct iteration method. So we calculate from Ax0, we calculate A1. Okay, we do the inverse, we calculate A1, and then from A1 from x1 we calculate x2, we calculate the inverse of those again, and then we keep doing the iteration. And then at each iteration we will check the convergence criteria. This is our convergence criteria. That is to check whether this value is smaller than this or not. To check whether this is smaller than this or not. If it is smaller than this, then we stop. Okay, then we stop the iteration. Sorry, we check the difference between the two solutions. We don't check this value. Okay, we check the difference. For example, here we check the difference between these two values. So we check the difference. That is to check the increment of the solution. If the increment of the solution is very small, then we stop the iteration. Otherwise, we keep iterating. Okay, so the second approach is to use the modified direct iteration method. Okay, so it's the same equation, but we use modified. So, and the first step is to assume the initial trial solution. This is same as the direct iteration method, and from using the initial trial solution, we calculate x1. Okay, we calculate x1. This procedure is also the same, but from the second iteration it will be different. From the second iteration, we need to first calculate delta x1, and when we calculate delta x1, we use the tangent, or we use the slope from the first iteration, and we calculate delta x1. Then delta x2 will x2 equals to x1 plus delta x1. Okay, and then we iterate, we keep iterate, and at each one. After we do each calculation, we check the convergence criteria. If it is met, then we stop the iteration. Okay, so this is the direct iteration method. It's easy to understand. I think it's easy to understand. You have to, and also in the slide, it's very good PPT slide. If you don't understand completely, please follow the slides after the lecture and to get the idea of the direct iteration method. The direct iteration method is used a lot in the FEM software. So whenever you do your own coding, maybe you sometimes you need to use the direct iteration method to solve the nonlinear problems, to solve the nonlinear equations. Okay, the second type of the method to solve the nonlinear equations is the Newton-Raphson method. Newton-Raphson method is also used a lot for in the mathematics and in the softwares. So the first order Taylor series for nonlinear equation. Okay, so we take this is the first order Taylor series of the nonlinear equation. Okay, and then this term we call it the tangent matrix. Tangent matrix. So the Newton-Raphson method is based on the first Taylor series for the nonlinear equation. And then let's have a look at the calculation procedure of the Newton-Raphson method. So we calculate the correction quantity. So this is our correction quantity. Then we use this correction quantity to update the approximate solution. Okay, so we have the correction quantity. This is our correction quantity. Okay, and then we calculate. How we calculate this? We use this equation. Okay, we use this equation. We use this based on this equation. Then you can get those. Okay, you can get those. We do the inverse of this. So here we are an plus 1 and k equals to those. And then we check, after we do this, we check the convergence condition. And if it's met, then we stop the iteration. Otherwise, we keep the new correction quantity and update the approximate solution. Okay. And so the iteration procedure of the Newton-Raphson method is the iteration procedure. Let's have a look. So first we give the initial value. So we start from the initial value, and then we determine the correction quantity. That's the delta A0. We calculate this based on the equation, and then we have the A1. Okay, then we have A1, and then we calculate the correction quantity here again. We calculate this, and then we have the A2. Okay, and every time you see, every time we are calculating, we have to do the inverse. Every time we have to do the inverse because the slope of those lines is changing. Okay, of those lines is changing, and you can see after several iterations it will converge to the solution. Okay, it will converge to the solution. So this is the procedure how the solution converge to how the calculation converge to the solution. And let's have a look at the convergence problem, Newton-Raphson method. So usually it has a good convergence. It usually have, but sometimes the divergence could occur. So as the possible divergence case. So we have the solution. So our solution line, and this is our nonlinear line, the red line, our nonlinear line. So we want to find the solution here. The solution should be here. Okay, the intercept of the curve, and this green line is the solution. So we start from the A0. Okay, we start from A0, and then we calculate the correction quantity. Then we have the A1. Okay, this is our A1. Then we calculate the correction quantity again. Then we have A2. So we see this is A1, A2, and A0, A1, A2. We see they don't converge. They don't converge. They are jumping around. So this is a divergence problem. This is a divergence case. Okay, and whenever you meet the divergence problems, maybe you should switch to a different method to solve this nonlinear equation. Okay. And then again, for the Newton-Raphson method, we have to calculate. We see here we have to calculate the inverse every time, and this is very expensive for the program, for the computer coding. Therefore, we have the modified Newton-Raphson method. So the modified Newton-Raphson method is to avoid calculate the inverse of the tangent matrix in the Newton-Raphson method. I usually apply the modified approach. For example, the modified Newton-Raphson approach, and we use the initial value as the tangent matrix. So here is the graph for the modified Newton-Raphson method. So we calculate the initial tangent matrix, and then we use the initial tangent matrix for the subsequent iteration. And so let's quickly have a look, go through the procedure. So we calculate the correction quantity of the approximate solution and update the solution. So we have the correction quantity. We have the correction quantity, and this we use the initial tangent matrix. We use the initial tangent matrix, and we calculate this. And then for each iteration, we check the convergence condition, and if it's met, then we stop the iteration. Okay. So this is similar to the modified direct integration method. So we don't talk too much here. And here, so we use an example to demonstrate the method here. So we have a nonlinear equation. Okay, we have nonlinear equation here. So where px equals to this, q equals to 3, and we also we rewrite and we calculate the tangent matrix. This is our tangent matrix. We take the derivative of p over x, and we get the tangent. We use this to do the iteration. Again, we assume an initial trial solution. Then from here we get key zero, and then from key zero we can get the using the Taylor series we can get the correction quantity. Okay, get the correction quantity. Then using the correction quantity on the initial value we get x1. We get x1, and then we keep to do the iteration, the second, and then we get the k1. So we use the xy, the value of x1, we put it into equation, then we get k1. Okay, we get k1. Then we use the same equation. We can get delta x1, and then use the x1 and delta x1. We get x2. Okay, then we keep to do the iteration, and at the same time we check the convergence criteria. At the same time we check this convergence criteria. If it is met, then we stop the iteration. Otherwise, we keep do the iteration. Okay. And then this slide is about the procedure to solve the same equation. Use the modified Newton-Raphson method. Okay, and it's the same equation as we see here. And this is the tangent value. And this is the initial tangent matrix value, and we keep using this one, so we don't calculate the new tangent matrix. And we pick the 0 as our initial value, and we put it here. Then we get the tangent is 4. Okay. Then we start our iteration. So we calculate the first correction quantity. Okay, first correction quantity, and the inverse of this will be 1/4. Okay, and then from the delta x0, then we can get x1. Then we use the same tangent, and then it will be 1/4. Then we can quickly get delta x1. This is our delta x1. Then we get x2, and then we keep iteration. At the same time we check the convergence, whether it's converged or not. Okay, so we can see using the modified Newton-Raphson method is much more efficient, because we keep the same tangent matrix, so therefore the calculation is more efficient, and if the solution become more complex, the efficiency will be more increased. Okay, and then the third types of method is called the incremental method. Let's have a look at the idea. So the idea of the incremental method is to divide the load into several steps, and then the displacement is divided into the same number of steps. So for example here, so this is and we can convert this to this one, and here this one is divided into several steps. Okay, it's divided into several steps. Lambda is a parameter to describe the change of the loads. So, and for the incremental method, we work out the derivative with respect to lambda. This is our lambda parameter, and then we have those. So from this equation, okay, then we to take the derivative. We have this one. Okay, we have this one. And well, here kt, so we call it the tangent matrix. Kt equals to dp dA. Okay, equals to dp dA. Okay. So for the incremental method, it converted into ordinary differential equation, and manual method can be used. So we have the differential equation you see here. So differential equation is also differential equation. So for the differential equation, we have many methods. So we have, for example, we have the Euler method, the Newton-Raphson method, which means we convert the original nonlinear equation into the differential equation. Then we can use the already established method to solve the problems. So the first is the Euler method to solve the the differential equation. Okay, this is a procedure of Euler method. So we give the initial value, then we use the follow equation to compute the next value. Okay, this is the compute. If we give this one, then we can compute those one by using this equation. Okay, and then also there's a correct Euler method. So we use the follow equation. We use the follow equation. This is the correct Euler method to calculate AM1. Okay, we know AM, so we calculate AM1. So this is a very brief idea of the method. If you want to know the details of the method, please check the books. And then it's the convergence of the method. So the Euler method, to avoid the drift of the solution, we use the follow equation to consider the balance correction. So for example, what does it mean, the drift of the solution? So for example, here we have A1, then we have this Q1, Q2, Q3, and we can say Q1, Q2, Q3 is getting farther and farther to the right line. So this is called the drift of the solution, which means is getting farther and farther to the solution. So this is the drift of the solution. So to avoid the drift of the solution, we use this equation to consider the balance correction. So we correct it. So this is the answer after we consider balance correction. So we have here and here, and then we do the correction, and we move to here. Okay, and then we do here, and then we do a correction here. We get this, and then we continue to this. Then we do a balance correction. We get this point. Okay, so this is a technique to avoid the drift of the solution. Under the Newton method, the procedure for the Newton-Raphson method. So in each increment step, we use the Newton-Raphson method to get the solution. Under the procedure of the Newton-Raphson method, we use the tangent matrix as the initial value of the current iteration. Okay, this is the modified Newton-Raphson method. So now let's have a look at the convergence of the Newton-Raphson method and the modified Newton-Raphson method. The modified Newton-Raphson method can avoid calculation the inverse of the tangent matrix. And the convergence speed was decreased. Okay, this is the modified Newton-Raphson method. We can say we use the initial tangent matrix. We use initial tangent matrix. Therefore, the calculation speed, the calculation efficiency is increased. But we say for these problems, we'll take more iterations for the modified Newton-Raphson method to converge to the solution. But for the original Newton-Raphson method, we can say it quickly converge to the solution. Therefore, that's what we see here. The modified Newton-Raphson method, they avoid calculate the inverse of tangent matrix, but convergence speed was decreased, especially when the PA curve, this is our PA curve, P is like a Y, A is like a X, the PA curve is close to flat, which means if we become very flat as this, and then the efficiency of this was really decreased. Example structure close to load limit will become very soft. The convergence speed will be very slow. So to speed up the convergence, some correction method like the active method can be used. Okay, so this is really only for you to know different methods and to get an idea of different methods. And to get an idea, and then when you do the FE analysis, you can have the idea how to pick different ones. And this last example is to use the incremental method to solve the nonlinear equation. Okay, to solve the nonlinear equation, we use an example to demonstrate. So we work out the tangent matrix with our tangent matrix, and then we have the initial trial solution, and then we start for the initial trial solution. Then we can get the tangent value, and then this is our tangent value. And then we work out the delta x0, and then we update x, and then we start the iteration again. Then we update x, we get x to 2, and then we keep the iteration until we converge to until the convergence condition is met. Okay, so please follow those slides to do your own calculation, and in order to understand the method, in order to understand the incremental method, because here we are doing the online course, therefore we cannot to do the calculation with you on the blackboard. But please, if you want to understand, just follow the slide to do the hand calculation yourself. Okay, that's all for this chapter. So for this chapter, we introduced to you several different methods to solve the nonlinear equations, and those are the methods used in the FE software. So why we introduce this, because we want you to know the difference between different methods, also the efficiency of different methods. Therefore, when you do your own analysis, you should know what's the difference of those algorithms, and why, in which case you should pick which algorithm. Okay, that's the main aim of this chapter. Okay, so thank you very much. I will see you next time.